So in this next segment, we've got some talks that look at some of the current state of the art in terms of hydrologic water quality modeling and transport of materials. First up is going to be Dennis Flanagan with USDA-ARS at the National Soil Erosion Research Lab. He's pre-recorded his talk, so I'm going to play that and hope that that will work fine. So let's see if it does.
Good morning, and thanks for this opportunity to speak with you today about some of the hydrology and erosion processes in a widely used soil erosion model. My name is Dennis Flanagan. I'm an agricultural engineer at the National Soil Erosion Research Laboratory. This is a shot of our building. Like last time I saw it in March or April, have not been in the office, have been working remotely from home. We'll be talking about in this talk important hydrologic and water erosion processes at the field and farm scales, specifically about the water erosion prediction project model, detailed hydrology processes in WEP and erosion processes in WEP, and then a little bit about WEP status and current projects. So basically what we're talking about in terms of hydrology and erosion events, looking at raindrop splash, thin sheet flow, then concentrated flows, and particularly in agricultural areas, which result in sheet and rill erosion, shown on the left here, and ephemeral gully erosion when we get to larger concentrated flows in fields. So the scales of interest that we're talking about are hill slope scales from about 100th to 1 hectare in size, up to from 1 to 1,000 hectares or so for field farm scales, so small watersheds in agricultural areas or other areas such as forested regions or construction sites, and channels such as ephemeral gullies or grass waterways. Important processes at these scales, precipitation and weather in general, so rainfall occurrence, the amount of rainfall, the duration of the storms and the intensity of the storms, surface hydrology, particularly infiltration, and runoff, subsurface hydrology, percolation, seepage, and lateral flow, hill slope erosion processes dealing with detachment by rainfall, shallow flow transport, rill detachment by flow shear stress, sediment transport, and sediment deposition, channel erosion processes as we go to larger channels, detachment by flow shear stress, again, sediment transport, and ephemeral gullies down cutting to non-erodible layers, and sediment deposition. So just a small hill slope region extracted from a small watershed area, the watershed shown on the upper left here. Just an area here that we have precipitation impinging on the surface, other parts of the water balancing with soil evaporation and plant transpiration, percolation to lower layers, infiltration of water at the surface and surface runoff, and then rill and inter erosion occurring. The Water Erosion Prediction Project. This is a large national project by USDA that began in 1985 to develop process-based erosion technology for use by action agencies and others, and was meant to replace USLE best technologies. The main model development was from 1985 to 1995, and the validated model with documentation was publicly released in 1995. There's been extensive model updates and interface and database efforts since then, and the USDA Forest Service is a major user, particularly for determining remediation efforts following wildfires. The Natural Resources Conservation Service has been working on an implementation project since 2013 to utilize WEP in its field offices. The model itself is a distributed parameter, continuous simulation, deterministic process-based soil erosion computer simulation model. Spatial variability in soils and or cropping and management systems can be easily simulated in multiple overland flow element hill slopes or in watersheds with multiple hill slopes, channels, and impoundments. It's targeted for application to hill slope profiles where overland flow results from rainfall, snow melt, and or irrigation, and sheet and rill erosion are the dominant processes. So hill slopes are typically up to about 100 meters long. and also targeted for application to small field farm watersheds up to about 260 hectares in size, to additionally estimate soil loss or deposition in channels, such as ephemeral gullies or grass waterways, and impoundments, such as ponds, culverts. This is just a screenshot of one of the interfaces we have. It's a Windows interface, and this is showing the ability to do spatial changes in management. In this case, we have a cropped area here and a grassed area on this steeper slope section, another cropped area, and then a grassed area at the bottom here, and showing the spatial soil loss results in this graph as well, and deposition values. Continuous model simulation, so we typically run the models for 100 years or more to allow for long-term interactions between the climate, cropping, management, and soil factors. Return periods can then be computed for precipitation, runoff, and sediment loss. We can then use these in probability risk analyses. Continuous simulations also provide the ability to examine impacts of other things such as climate change on the complex hydrologic and erosion processes, and the model can also optionally be applied to individual storm events. And these are just some outputs from some simulations just to show continuous simulations. The top graph is a precipitation at a location in Minnesota over 20 years. You can see the variability daily in precipitation amounts. The center graph is of runoff, and the lower graph is of sediment loss. So you can see that the greatest rainfall does not always produce the greatest runoff amount, and also the greatest runoff does not always produce the greatest sediment loss. So this kind of demonstrates the effects of the interactions of climate, crop growth, soil disturbance, soil moisture levels, and residue cover amounts that are really going to impact what's happening in terms of the runoff generation and the sediment loss that occurs from storm events. Another example is some return period analysis results, looking at, in this case, on the upper graph, showing the return period values for daily sediment leaving a slope profile that's under conventional tillage. In this case, we had basically we had a 50% risk that the event soil loss would exceed 19 tons per hectare, 4% risk that the sediment loss would exceed 57 tons per hectare. Those are very large values of soil loss. For the no-till cropping on the bottom, I'm not sure you can see it when I'm doing this video recording, but basically much lower values. So basically only a 4% risk that your daily sediment loss would exceed 5.1 tons per acre per year, or tons per acre in that event. Precipitation, let's talk a little bit about the processes themselves that the model simulates. WEP can accept either direct breakpoint precipitation inputs, or more commonly it accepts standard Clygen outputs. Clygen stands for climate generator. It's a stochastic weather generator that can provide a string of daily long-term synthetic climate that approximates the long-term observed weather station statistics. It uses a two-stage Markov chain to determine the number and distribution of precipitation events. The weather station values include monthly values for two conditional probabilities: the probability of a wet day following a dry day and a dry day following a wet day. Other equations in Clygen are used to determine the storm depth, storm duration, the time to peak, and the peak intensity from the weather station statistical values. WEP typically uses this stochastic generator. The database contains 2,765 stations with a temporally consistent values from the recent 40 years of 1974 to 2013. Clygen produces 4 basic daily storm inputs, which are storm depth, storm duration, the ratio of the peak intensity to the average intensity, and the ratio of the duration where the peak intensity occurs to the total storm duration. Internally within the WEP model, the storm is then disaggregated into multiple intensity duration breakpoints that approximate a double exponential storm shape. And then the storm breakpoint intensity values are used in the subsequent infiltration, runoff, and erosion calculations. Another input option to WEP utilizes storm breakpoint precipitation, time and cumulative daily precipitation to that time directly. So this might be observations from a recording rain gauge at an experiment site. This graph just shows a hypothetical double exponential storm where we have time to peak shown as this time over the total duration, the IP, which is the peak intensity over the average intensity. We have time varying rainfall, and the average intensity is the total precipitation divided by the total duration of the storm. How the model works: from the climate input, we determine if rainfall occurs on a simulation day. And then if rainfall occurs, we determine the storm characteristics and the breakpoint rainfall inputs to the hydrology component of the model, calculate infiltration and any surface runoff from the storm. If runoff occurs, we determine the effective rainfall intensity, the peak runoff flow rate, and the flow shear stress from those. We calculate the sediment load down the hill slope profiles at a minimum of 100 evenly spaced points, and then determine the net soil loss or deposition at each point and the sediment leaving the profile. We tabulate and store all temporal and spatial soil loss and sediment yield values for each storm for use in the output results in the statistics. We update infiltration and erodibility parameters daily based on any soil disturbance from tillage, changes in soil moisture, plant growth, and residue decomposition. And then we go back and start on the next day. Go back to step 1. So this graph again shows the instantaneous rainfall intensity. The red line is the time varying infiltration based on the Green-Ampt-Mein-Larsen equation, affected by capillary potential, soil moisture deficit, and effective hydraulic conductivity. And then our runoff rate is the difference between the rainfall intensity and the infiltration rate, so this light blue line here. The erosion and sediment transport is calculated based upon this peak runoff rate over this time. So the time is an effective duration that matches, so that the area under the curve matches the area under the actual runoff hydrograph curve. So we preserve the volume runoff. Surface hydrology in the model. As I mentioned, we use a Green-Ampt-Mein-Larsen infiltration equation modified for unsteady rainfall. Infiltration is a function of the soil capillary potential, moisture deficit, and effective hydraulic conductivity. Runoff is predicted from the rainfall excess adjusted for surface depressional storage. The runoff rates are then predicted using a kinematic wave equation. For single storm simulations, the model calculates the entire runoff hydrograph. In continuous simulations, an approximate method is used to only determine the peak runoff rate that's needed in the steady state erosion calculations. An effective rainfall intensity is calculated based upon the summation of intensities during all the periods where the runoff is generated in an event. And a full water balance is calculated daily, and water can also leave the slope profile through soil evaporation and plant transpiration. Subsurface hydrology, the soil is divided into layers. The top 2 are 10 centimeters thick. The remaining layers are 20 centimeters thick, down to a maximum depth of 1.8 meters. Infiltrated water in excess of field capacity, water content is percolated to the next lower layer, and the water can exit the bottom of the soil profile as deep seepage. Plant growth and roots can extract water from the subsurface layers, decreasing the soil moisture content there. And the subsurface lateral flow is also calculated, and subsurface water can exit the bottom of a hill slope and contribute to channel flow. Tile drainage can also be simulated in WEP to reflect effects of artificial subsurface drainage on reducing soil profile water contents. This is the main equation for hill slope erosion. The model uses a steady state sediment continuity equation that assumes the storm's effective rainfall intensity and peak runoff rates can be used with effective durations to represent the erosive potential. So the change in sediment load with distance is the summation of the rill detachment deposition rate plus the interrill sediment delivery rate to the rills. Rills are assumed to be regularly spaced rectangular channels in the model. So basically on the right here we have these regularly spaced blue rills, and then the interrill areas between them supplying water and sediment. The rill detachment equation, when the transport capacity of the flow is greater than sediment load, is shown here. So a rill erodibility times the difference between the flow shear stress minus the critical shear stress times the sum of the 1 minus G over TC. So this is the ratio of sediment load to transport capacity. As the flow becomes filled with sediment, the detachment capacity will decrease. This just shows the changes in the real detachment rates based on the soil conditions. So a freshly tilled conditions has the greatest real erodibility and the lowest critical shear stress. Once that soil consolidates, the critical shear stress will increase, the erodibility will decrease, and under a long-term no-till, you may have the highest critical shear stress and the lowest real erodibility values, so the least erodible conditions. Sediment detachment and sediment delivery to rills. So again, looking from the side here, we have these inner rill areas supplying water and sediment to the rectangularly shaped rill channels. This is the inner rill detachment equation. So an inner rill erodibility times the product of the effective intensity and the runoff rate on the inner rill areas. There's a slope adjustment factor and some other adjustment factors that are applied. Sediment deposition occurs when the sediment load exceeds the transport capacity. This may be due to slope concavities or an increase in surface roughness due to different vegetation such as grass buffer strips. This is the real deposition equation here. Basically, a difference between the transport capacity and sediment load times a rainfall turbulence factor times an effective fall velocity divided by the flow discharge per unit width. Current status in projects, the model is actively maintained and updated at the erosion laboratory. Major current effort is assisting NRCS with implementation, including development of web-based interfaces and databases. Efforts continue with Purdue graduate students that involve improvements in sediment transport calculations, improvements in subsurface drainage representation, and addition of water quality calculations to WEP. Work in the past 2 years has also involved some extensive comparison studies between WEP and Russell II erosion predictions. And we're also collaborating with other groups on use and application of WEP technology, including the Daily Erosion Project at Iowa State University. Just some screenshots. This shows the new NRCS WEP web interface for hill slope simulations. The user has outlined this field here, automatically then determines the location for climate inputs, the soils that are available there, latitude, longitude. This is the main screen, again showing the location, soils. The user can input the slope shape, steepness, aspect, the length of the profile, management system being used, and then run and get the simulation results. And there's also special reports that are produced for NRCS. This screen shows the watershed application using another interface, another web-based interface for WEP, and we're also developing a new one for NRCS. This is for a EPA watershed application near Cottage Grove, Minnesota. And this is showing spatially what each of the different hill slopes in this watershed is contributing in terms of the amount of sediment, in terms of predicted tons per hectare per year. In summary, process-based models allow simulation of important physical processes. Fundamental physical processes related to hydrology and erosion are represented within the model code, and continuous simulations with the model allow for effects of multiple interactions between climate, soils, and cropping management systems. Long simulations also allow for return period and probability risk analyses. Work continues to expand the model applications with the Forest Service, NRCS, and others. And that is the end of my presentation. I would be happy to answer any questions that anyone might have. Thanks very much.
Dennis, thanks. We do have time for a question or two, so questions for Dennis.
Dennis, I had a question about the, you mentioned the very long-term simulations, 100 years plus.
Yes.
And I was wondering, do you have any functions to reflect changes in soil structure that might happen over the 100 years, in particular related to organic accumulation or depletion, but also hydraulic conductivity, cascading effects on hydraulic conductivity, suction at the wetting front, for Greenham. So is that dynamically adjusted in time, or is assumed to be like in the initial conditions?
We currently are assuming based on the initial conditions, so we do not have that functionality in the model. There's people that would really like to have that functionality in the model, but currently we don't have that. So,
thanks.
Another question for Dennis?
So, Dennis Pat Havens here. What would it take to introduce a chemical component? We're talking about eroded sediment and water going off. Has anyone tried to introduce either a nutrient or a pesticide transport component into WEF?
Yes, we've actually been working on that for a number of years. We have had a graduate student here at Purdue that, well, actually before that, we had one of our ARS scientists, Reza Sababi, working on that when he was in Florida, and has had added for single OFE hill slopes the capability using some of the SWAT chemical transport routines. And then more recently had a graduate student at Purdue working on that, and currently Ryan McGehee, who is on the conference here, is working on multiple OFE and channel component pollutant transport within WEF.
Jeff, are you set to share your screen? So if you want to go ahead and get that started. So I think we probably should thank Dennis. So Dennis, thanks. The recording worked well, so appreciate you doing that. And thanks for answering some questions. And I know you'll continue to be around.